So, I continue with the pulse propagation process in amplifiers. So, when let me talk about the small signal gain. Okay. A small signal gain, as I had said before, that when the signal, the pulse, the initial pulse is very tiny, then it sees a certain amount of gain which I called as G0. So, here I take the case. So, Frank-Northwick formula was a general case, and you can always reduce it to E out equal to E I in e to the power G0 L. Okay. So, this is what the Frank-Northwick thing reduces to when E I in is much less than E saturation. That means my input signal is very small, and then my output signal turns out to be E out is equal to E I in e to the power G0 L. I do not know, just try to recollect from lecture 3 and 4, approximately somewhere like that, where I had described to you the Einstein's coefficients, and then we had come to the flux change in as it travels through a medium, an amplifying medium. Okay. So, there I think it was somewhere like S is equal to S0 e to the power alpha L or Z, I had put it as Z. Okay. Just try to recollect this formula from lecture 3 and 4. So, here if you can see these two are just the same. Alpha is the same as G0 and Z is the length along which the beam is travelling. Here L is replaced by L. Okay. S0 is the initial flux, I had called it flux at that time, but okay, it could be energy EIN. So, these two are very much similar. Okay. So, here in this case, and then we had this happens, this small signal, it happens very easily in a oscillator. Where this is the oscillator and you have a small pulse which is making lots of round trips here, maybe 60 to 70 round trips, okay, before the laser comes out. Okay. So, in case of an oscillator, at the end of those 60 to 70 round trips also, the signal is actually not, it is not very close to E sat, it is much lower than that. Okay. But once it comes into an amplifier, you already have a pulse here which has substantial energy, okay, and this goes into an amplifier, but it's already got so much of energy that it depletes the population inversion very easily. While in case of an oscillator over 60 to 70 round trips also, the initial gain remains as it is G0L. The change is negligible, okay, it is as good as that, or there is a repeated replenishing of the gain. So, this in an amplifier what happens is when EI in is much less than E sat, then you have this small signal gain like this. So, you can write E out will be EI in e to the power G0 L. Now, suppose EI in becomes much more than the E sat, then what happens is Frank-Northwick's equation reduces to this. You can actually do it quite easily. Suppose you take it reduces to that. Suppose you take the initial equation is E out is equal to E sat ln of 1 plus exponential EI in upon E sat and then e to the power G0L minus 1. Okay. So, yeah, okay, that is the, just check in that, yeah, E sat ln of 1 plus exponential E I in upon E sat e to the power G0L minus 1. Okay. So, I have just written it here once again. Here actually this part is so large that you can forget about 1. Okay. Just forget, this part is EIN is much larger than E sat. So, 1 is negligible. So, forget about this part. Then what you do is, so you have E sat ln of only this exponential part and this exponential part. So, you can use the identity of ln of a b is equal to ln of a plus ln of b. You just use that identity and then you will finally come to this equation. Okay. This is what it is. You will finally come out to this. Okay. So, that is how it is done. So, in case of E I in much greater than E sat, this is the value. Just have a look at this equation. E out is E I in plus this part. The second part is not very large, it is just some additive value. Okay. So, for some part of the pulse as it goes into the amplifying medium, you will get some additional energy which is added to this input E I in, but as it goes through this becomes smaller and smaller, and then E out becomes equal to E I in. So, the input energy has not increased at all, while if there is a small signal gain here, the output energy is exponential of the there is an exponential factor to this input energy. Okay. So, basically it is amplified exponentially, while if E I in is much greater than E sat, then it is not an exponential, it has just a logarithmic part to addition to the input energy, and that is not what we want, but that is what happens when more and more energy is getting extracted, and at some point that energy is greater than E saturation. Okay. This is the idea of saturation. You have to take that saturation into account when you are designing your amplifier systems. Okay. So, generally what will happen is, now suppose you want to reduce the energy. Suppose this is one amplifier, amplifier 1, and the laser beam is going into amplifier 2. One thing is, intuitively also you can see that, one thing is you can defocus the beam. Defocus the beam and let it go into this amplifier. So, a larger part of the amplifier is presented to the laser beam to be amplified. Okay. So, whatever is the spot size here, suppose it was this small, you have to make it bigger. So, that means your energy has, the total energy is the same, but the energy density is different. So, these formulas here, of course, I have talked only about energy, but you can apply it very well for in terms of energy density or in terms of intensity. Okay. So, the formulas remain just the same. So, here if I defocus the beam, the intensity becomes less or the energy density becomes less, energy per centimeter square becomes less, okay, and it goes into this beam and it sees the gain G0 once again. You do not have to use the term G effective at that point. Okay. So, this is one way of extracting more energy by defocusing the beam. Okay. So, these kind of optics has to be used within your amplifying system. Okay. Let me give you, okay. This is the long amplifier chain, okay. A schematic of this long amplifier chain and all the optical systems that are involved in a amplifier chain. It's not as simplistic as the first one which I showed you. This is a slightly more system which is more close to the reality. Okay. So, in what I show here is, this is the oscillator, then there is pulse selector, and then there is amplifier 1, amplifier 2, amplifier 3. Okay. The laser beam is shown by this blue arrow, it is going this way, this way, this way, and it comes here, comes here, comes here, and you can keep on increasing the number of amplifiers depending on your needs. Okay. Now, what I have shown in the previous slide here, that means you have to do something to the beam spot size in order to extract the best amount of energy. So, this part is a representation of there may be a concave, convex lens, concave lens, so that you manipulate the beam spot size and it fills in the whole amplifier. That spot size is such that the beam fills in this total amplifier. Suppose it is a ND glass rod and the whole diameter of the rod, it has filled it in completely. And once it fills it in completely, it can extract the best amount of energy. Okay. So, this kind of represents the other passive optics that you require in order to let this whole chain, MOPA chain, work smoothly. Okay. So, here the oscillator, here I have shown this is the active medium, this is the modulator, which you know before the oscillator. So, there is a modulator here, so you get a train of pulses which comes out, and the modulator is an acousto-optic loss modulator driven by RF. Okay. So, when you have such a acousto-optic loss modulator, then it is kind of an active modulator, and each pulse will be in the pico-second range, pico-second to nano-second range, and there will be a train of pulses and you choose one of them because you are going to amplify just one of them, you need only one. So, you have a pulse selector which will select one out of that train and it passes it on again to these amplifiers. Okay. So, now you have a pico-second range pulse, but then in an amplifier which is pretty short, okay, depending on the modulation. But anyway, it is supposed to be a long pulse, okay, in the nanosecond range. And even if you start off with the pico-second pulse, then also as it travels to the amplifier, it has changed its pulse length to a nanosecond. So, your final pulse output would have changed over to a nanosecond pulse. Okay. So, these are the things that you have to bear in mind and see how these parameters can be selected or modulated in order to have the best output for yourself. Okay. So, it's the whole process of this laser chain is like a trade-off, like there is between the carbon dioxide part and the ND glass part, there was a trade-off between them and we finally chose ND glass. Here also, suppose this is a ND glass chain. Here also at every point you are making a compromise on something, okay, before you come to the final pulse. Okay. So, you have got to monitor all these parameters at different stages of the amplifier. Okay. So, here what I have shown is in this amplifier, you just put a beam splitter here. So, part of the beam shown in red goes into the beam profile monitor and and the rest of it, a very small part. This is kind of a diagnostics for this laser chain, and the rest of the beam is going into the next amplifier to get amplified. So, in case of this beam profile monitor, it monitors the beam which has come here. So, my input beam here, this is the input beam, which looks like a pretty regular beam. It has the maximum intensity at the center or the maximum energy at the center, and the outer wings have lesser energy, say a kind of a Gaussian profile. Maybe something like this, okay, which is relating to this. Maximum intensity is here at this point and lesser in the wings. Now, you see the ones in the wings, if you are reaching the saturation point, the part of this pulse, the cross section of this pulse which is in the wings is extracting really much higher energy than in the center. When this center part reaches a saturation energy, the center part will reach the saturation energy first, and the wings will still be extracting. So, there is uneven extraction even in this case. So, it happens even in the realm of time, and it happens in the realm of space. So, in both the spheres, time and space, there is a differential extraction of energy from the amplifiers. So, this is what has to be monitored and checked and continued on. So, here actually in this beam profile, what I am trying to show is it gives you a diagnostic of what happens in this amplifier. Here what you see, the beam has broken up into these 4 parts here. It is no longer the same. It has passed through an amplifier, and this is what has happened. And you know, this happens even when the amplifier is off. I mean, you are not passing any pumping system into it. You are not pumping it with flash lamps. So, the pulse itself is giving rise to some nonlinear effects within that amplifying medium. The ND glass itself works like a nonlinear medium, because the pulse has pretty high intensity by that time. And then this is what is happening. You are breaking up into this 4 kind of, these are called conoscopic patterns, by the way. It could also look like this, it could look like this one at the bottom. This is monitored by a different beam profiler. It is a piece of thermal paper. So, that is why they are looking a bit different, but the effect to be shown is you started off with a decent looking spot, and the spot has become like this. Okay. And this is not what you want. This becomes a very divergent beam. It will diverge and just go out. Even the optics that you use may be of no use after some time, after a few amplifiers. And then if you have a spot something like this at the end of the laser chain, you won't be able to focus it to a point onto the target. It is impossible to focus this onto a target, into a small point. Okay. So, you have to deal with these non-linear effects also, which come into this amplifier system. Another non-linear effect that comes in is beam focusing. Try to recollect the third order non-linearity of beam focusing or lens-like effect that takes place. So, you have this laser beam, it focuses to a point within your amplifying medium, and then it has caused a destruction in your amplifying medium itself. It can cause, suppose you have an amplifying medium, it can cause streaks of light. That means the beam has focused onto these streaks of light. And you don't want that. And this is not the kind of thing that you want. It will destroy your ND glass system. See, again, this in case of carbon dioxide, such things don't happen that easily because it's gas filled. So scalability was better in a carbon dioxide. Scalability was not so good in ND glass systems. Okay. So you have to take care of the nonlinear effects. Then another effect that you have to take care of is the spectrum. Okay. So here is my amplifier. I take out a small part of the beam just to check how the spectrum has changed. Has it changed too much? The initial spectrum that I started off with, has it changed too much, or has it become, it is still workable? I'll tell you what happens in a spectrum analyzer. Yeah, you are recording the spectrum, of course. So you start off with a certain spectrum. This is a frequency. Okay. And your laser action is in the central frequency. These are also there here. But what happens is here at the center, you have taken out that gain from here. The laser, the input seed pulse has taken out the gain at the center. While this other parts of it, when there is a hole here, they replenish this hole, all that population can go in here, and then you can extract at the central line itself. But while it is doing that, this is changing. Okay. There is something called gain narrowing. So all this is coming into the population on this part and this part. They are all filling in the hole here. Okay. And so the gain along this side and along this side has become less. So the spectrum has sort of narrowed. And if the spectrum has narrowed, even the gain has narrowed. That is called gain narrowing. That's why you need to monitor the spectrum. Here. These I have just put down the problems to be overcome, which I have said in the previous slide. So in the previous slide I spoke about the birefringent effect. This is the birefringent effect. This happens because of birefringence that is induced in the amplifying medium. Okay. This pulse spot size breaks up into all this. It can be explained with the help of E ray and the O ray and the interference between E ray and the O ray. So your initial pulse or initial light has broken up into two perpendicularly polarized light, and when they interfere, this is the outcome. Okay, so this is the birefringent effect in the medium. So that's what I say here, the birefringent effect. It gives rise to large beam divergence, which is unwanted, and those patterns are called conoscopic patterns, and these conoscopic patterns itself will be amplified, and the divergence will grow and grow. And when the divergence grows, then it becomes impossible to propagate any more. Okay. So birefringent effect gives large beam divergence, which gives rise to this conoscopic patterns which you see onto the spot size, onto the cross section of the beam. Those get amplified, you get even larger divergence, and then you are unable to propagate further. Unable to propagate further, you don't extract energy. and you do not even have a decent looking beam outside. By decent looking, I mean a Gaussian shaped spatial profile, okay, which is the ideal profile for focusing the beam onto a small spot size. Now, in case of gain narrowing that I mentioned, here gain narrowing. In gain narrowing, one problem is, okay, the gain has narrowed, you have selective amplification. That means only the center line, center frequency is getting amplified, because the side ones are falling into that hole of the spectral profile. So, you have selective amplification, and this affects your pulse spectrum. As you can see, the spectrum becomes narrow and narrow. The spectrum becomes narrow means the gain is also narrowing. So, the pulse spectrum is narrowed, dependence on gain medium, okay. And remember, the time bandwidth product limits on shortest achievable pulse. Time bandwidth product, if you remember, delta nu delta tau, okay, is almost equal to 1 or 0.4 or something, okay, a small number. So, what it shows is, if time bandwidth product, that if your delta nu, that is the full width half maximum of your spectrum, is large, then your time becomes short. If your delta nu is getting narrowed, becoming smaller and smaller, then your delta t is becoming larger. So, here again you started off, say, with a picosecond pulse, but because of the gain narrowing, it has become a nanosecond pulse. Okay. So, that's one problem here. So, making this laser chain has a lot of problems to be overcome. I have just given you 2 of them. They are very important ones. Then there are many other smaller problems to be overcome before you come to this final laser output beam for fusion. Okay. So, next time I will go ahead to tell you about how newer and newer pulse systems are being made to extract more and more energy. Finally, as I said before, the world is crazy to extract more and more energy, but how to do it? Okay. Where is the bottleneck and how to overcome that bottleneck? That is what we will discuss next time.